Hello all, in this presentation we'll be presenting PaperW8, our proof of concept IoT ransomware which can be used to attack many different types of IoT device. First, we'll cover some of the background relating how ransomware can affect the Internet of Things. Next, we'll show how PaperW8 works, followed by the devices that we tested it on, the results, and the video demo. Finally, we'll provide some countermeasures and summarize our findings. Ransomware is a type of malware designed to extort a victim through the restriction of their valuable data. To regain access to their data, the victim must pay the ransom, normally with cryptocurrency such as Bitcoin. Some ransomware variants are also moving towards threats of exposing data in order to solicit payment from their victims. Consumers, manufacturers, companies, and entire cities have been hit with ransomware attacks across the world. A city in Florida had its water pump stations taken offline, forcing residents to make utility payments via mail. The council eventually sent $600,000 to attackers to regain access. The NHS was attacked by WannaCry, which caused an estimated £92 million in damages. NotPetya paralysed several multinational companies by encrypting the master boot record of infected systems, resulting in an estimated $10 billion in damages. Most recently, in June 2020, a university in California paid attackers $1.14 million for decryption keys after being hit by ransomware. The Internet of Things is a network of embedded devices and sensors connected to the Internet, allowing them to communicate, interact, and share information. Some examples of IoT devices include surveillance cameras, virtual assistants, DVRs, and smart TVs. While it can be argued that any device that can connect to the Internet could be considered an IoT device, in the context of this work, we consider an IoT device as an Internet-connected device with constrained capabilities designed to perform a predefined function. The Internet of Things has been targeted by many families of malware with varying purposes. Two relevant pieces of malware, Mirai and Brierley, have targeted a large number of IoT devices in the past. Mirai, arguably the most well-known IoT malware, was used for several powerful distributed denial-of-service attacks and infected over 600,000 IoT devices. Unfortunately, the source code has also been released publicly, leading to multiple variants being developed, adding new exploits and functionality. Brierley, a lesser-known IoT malware, takes a different approach. Its only goal is to disable the infected device, preferably permanently. It runs through a list of predetermined shell commands aiming to corrupt local data and throttle services, such as network access, to near unusable levels. There have been several previous attempts to implement ransomware on various IoT devices. Researchers at Avast demonstrated that an attacker could compromise a smart coffee machine, allowing them to display ransom notes, boil water, and run the grinder without any user interaction. An LG Smart TV was disabled by malware that originally targeted Android-based phones, which eventually required LG support to provide an alternative method to perform a factory reset. At DEF CON 24, pen test partners demonstrated their process to modify the existing firmware of an IoT thermostat, which would allow attackers to show a simple ransomware message, lock out the victim, and modify the temperature in their home. While these approaches are valid examples of ransomware that could potentially be profitable, there are a couple of issues that might prevent them from being used in a practical setting. The previous examples targeting Linux devices were creative in how they locked down and ransomed the device, but were also designed to work specifically on that model of device, which greatly limits the potential targetable devices and therefore the total likely payout. Additionally, each previous example seems to require persistence. The methods required to gain persistence on other IoT devices may not be possible, or will require significant works to be made compatible. To address these limitations, we created PaperW8, a proof-of-concept IoT ransomware that targets exploitable Linux-based IoT devices. It had to be generalizable, as the targets may vary drastically in architecture, brand, and purpose. As such, it should be easily extendable and require as few modifications as possible to support new devices. In order to simplify the infection process, it must also not require persistence. Finally, it must have some method of communicating with the victim, as otherwise PaperW8 will be unable to demand ransom. Our goal was to identify possible roadblocks that attackers may face when developing ransomware, and assist in the development of countermeasures. This is the overall structure of PaperW8. At first glance, it may look a bit complex, so over the next few slides, we'll break it down into the main 4 stages: exploitation, communication hijacking, encryption, and recovery. PaperW8 is capable of running on a variety of devices with differing purposes, architectures, and sensors. However, in order to run, it must first obtain shell access. Gaining this access remotely normally requires a vulnerability on the device that can be exploited by an attacker, such as a command injection or an open telnet port with a weak password. After exploiting the targeted device, the next step is to upload any required dependencies based on the device's functionality and architecture. To do this, PaperW8 will use a TFTP or Trivial File Transfer client, which is often present on IoT devices to download remote files to local storage. For our proof of concept, we assume that the attacker will run a TFTP server that holds all of the required binaries PaperW8 will need to run. If TFTP is not present, we can use a technique called echo loading, which we'll briefly cover later on. Once the required dependencies have been downloaded onto the device, the attacker can move on to the next stage, hijacking the communication channels. One of the largest issues IoT-based ransomware faces is the act of communicating with its victim. Desktop PCs have a reasonably standardized method of communication that is almost guaranteed to be present: the monitor. IoT devices, however, have no such guarantee and can communicate with users in a variety of ways depending on their available outputs. PaperW8 aims to hijack these methods of communication to instead send ransom notes requesting payment. This not only provides a method of communicating with a user, but also prevents the victim from being able to use the device effectively. When testing PaperW8, we use 3 different hijacking techniques to communicate with a victim. If a device makes use of a web server as an interface, PaperW8 can replace it with its own and display a ransom note instead. Additionally, if the device that is infected is a router, PaperW8 can also reconfigure the DNS server to redirect all HTTP requests to the hijacked device. If the infected device makes use of a graphical user interface, PaperW8 can also hijack the frame buffer to display a ransom note on any attached screens, preventing the interface from being used. The attacker can then close any other running services, including those that contain the vulnerability that originally allowed them to gain access. This will make it very difficult for the victim to regain control of the device. After hijacking the various communication channels, PaperW8 then aims to encrypt the important files stored on the device. Traditional ransomware that targets desktop-based computers aims to encrypt unique files that may have value to the user, such as databases or Excel documents. IoT devices, however, are unlikely to be storing any user-generated files of value to the user. While there may be some exceptions, such as with wearable devices that may store personal information, most IoT devices will only contain files that are used to configure or run the device. Instead, in order to ransom a device effectively, PaperW8 targets the functionality of the device itself, which will always have some value to the user. In order to do this, it needs to find a way to permanently disable the devices it infects. IoT devices often use flash memory to store all of the required data to run the device. This data is often separated into partitions based on its contents, such as the bootloader, the file system, or configuration files. However, how these partitions are set up will vary based on the device. The developers may choose to have multiple file systems or configuration partitions, for example. In Linux, the flash memory and its partitions can be accessed via the Memory Technology Device Subsystem, or MTD. By reading various files exposed in the file system, we can understand how the flash chip is laid out. For example, if we read the /proc mtd file, we'll be provided a list of partitions, their sizes, and their user-defined name. We can use this information to get an idea of how the device might be structured. PaperW8 can then use mtd block files in the dev directory to access the raw contents of any of the available partitions. Importantly, not only can these files be read, but they can also be written to, such that an attacker can make persistent edits to the flash memory from the shell. In our proof of concept, we target the bootloader partition. PaperW8 reads the bootloader partition into a buffer, encrypts it using AES, then writes it back to the same partition. This will mangle the bootloader such that the device will fail to boot if it is restarted. At this point, PaperW8 will have taken full control of the device, while restricting the victim's access. The device can be easily recovered by PaperW8, as it still has access to the decryption keys and the flash memory until the device is restarted. Recovery would be extremely hard to achieve without specialist tools and knowledge. The victim is unlikely to have any reasonable alternative, thus leaving paying the ransom as the only easy method of recovery. If the ransom is paid, PaperW8 can simply reverse the process to recover the device. By decrypting the mangled bootloader, then restarting the device, it should be able to boot as normal. As PaperW8 resides purely in temporary memory, it will also be wiped when the device is restarted. As part of our research, we exploited and successfully ransomed 6 test devices which have previously been targeted by IoT malware. PaperW8 was able to hijack methods of communication and brick all 6 devices, such that the average user would not be able to recover them, despite their different purposes, brands, and architectures. Using the device's factory reset function was not enough to recover them from a brick state, except for in the case of the R6250 router, which had a feature which, while not mentioned in the official manual, could be feasibly achieved by a knowledgeable user without any specialist tools. Here we will demonstrate PaperW8 being run on 2 of the test devices. First, we will show PaperW8 being used to take over an HG532 router. On the right hand side, you can see the admin panel of the router, where a user would be expected to change any of their chosen configuration settings. On the left, we'll run the malware step by step so you can see it in action. First, we use an exploit with shell commands to upload all of the required dependencies and replace the web server with our ransom message. Next, we telnet in on an open port to show the bricking process. We use an application we named mtdedit to encrypt the bootloader partition with simple XOR encryption. We then physically reboot the device. As you can see, our computer is trying to reconnect, but is not successful, and the router is no longer responding. At this point, the router can be considered bricked. The WIPG1000 is a presenter used to allow users to stream presentations on the same network. Here, we will demonstrate one of the later versions of PaperW8 being used to hijack its various communication channels. Here, we have connected the presenter to a router and a monitor. A configuration page is also available at the IP displayed on the screen, which can be seen on our attacking machine. We run the exploit that will allow the attacker to gain shell access. As the device does not have a TFTP client natively installed to download the dependencies, we will use a technique called echo loading to upload a TFTP client from our attacking machine. This uses a series of echo commands to rebuild the binary 50 bytes at a time over telnet. Once the client has been uploaded, it can then be used to download all the required dependencies, which can then be executed. As you can see, the attached screen has been hijacked to display a simple ransom note. Additionally, it directs the user to access the IP of the device from a web browser for more information, as the configuration page has also been replaced with a ransom note. There are several countermeasures that we believe will be effective in preventing our proof of concept attack from succeeding. Firstly, if developers do not need to update certain partitions, such as the bootloader, forcing them to be read-only could prevent attackers from encrypting important static information. If the bootloader could be restored via the factory reset process, the victim should be able to fully recover the device when partitions are encrypted. While they may lose their configuration settings, it will allow them to recover the functionality of the device. However, this may require the factory reset to work independently of the main system. When attacking each of the test devices, we needed to gain access to the MTD subsystem files to make modifications to the flash memory. If root access was required to write to important partitions and applications were run at a lower privilege level, attackers may be prevented from making device-damaging changes. Finally, users should update their devices regularly to patch known vulnerabilities, preventing attackers from using exploits to gain access. In summary, we investigated the viability of ransomware on IoT devices. We proposed PaperW8 to demonstrate how an attacker may overcome various limitations of Internet of Things devices, such as a lack of easy communication methods and valuable files. To demonstrate the viability of the attack, we tested PaperW8 against 6 devices with varying purposes, hijacking their communications and bricking them, preventing easy recovery. Finally, we proposed several countermeasures that we believe will prevent this type of attack from succeeding. Thank you for listening.